Hello everyone, welcome to this video on work, power and energy. Work. When a particle is displaced by the action of external force along a definite curve, the line integral of the force along the curve is called work done by the force. In mathematical form, we can write W equals integral along the curve vector F dot vector dr. Here vector F is the external force, dr is the displacement vector, and W is the work done by the force along the curve C. The force are divided into two types, first conservative force and second non-conservative force. Let's define the conservative force. If work done by a force on a particle depends only on the initial and final position and not on the path along which it is displaced, the force is called conservative force. As the work done by conservative force only depends on initial and final position, the work done in round trip becomes zero. This is another definition of conservative force field, which states that if the work done in a round trip is zero, the force is conservative. Mathematically, we can write the force is conservative if closed integral of f dot dr equals 0. Non-conservative force. If the work done by the force on a particle in a round trip is non-zero, the force field is called non-conservative force field. The work done by non-conservative force field is dependent on the path along which the particle is displaced. Mathematically, we can write the force is non-conservative if the closed integral of vector f dot dr not equals to 0 along the curve in the round trip. Kinetic energy. The energy of a particle or system of particle because of its motion is called kinetic energy. Kinetic energy of a particle is defined as k equals half mv square, where m is the mass of the particle and v is the velocity of the particle. Potential energy. The internal energy of a system because of the position is called potential energy. The potential energy is defined as negative of work done by the conservative forces in bringing the particle from reference point to the current position. Mathematically, we can write uf minus ui equals minus of integral I to f vector fc dot vector dr. Here vector fc is the conservative force and vector dr is the displacement, and I corresponds to the initial position and f corresponds to the final position. So the potential energy at final position with respect to initial position is minus of integral I to f fc dot dr. So we can see that the potential energy term, which is in left hand side, is denoting the change in potential energy. So the formulation is for change in potential energy, not for the absolute potential energy. We always define potential energy with respect to some reference position, which is denoted by the symbol I. So the potential energy is a relative term which denotes the change in potential energy from the reference position. Work energy theorem. The work energy theorem states that work done by resultant force equals change in kinetic energy. Consider a particle on which the forces F1, F2, F3 and Fn are acting. The resultant force on particle is vector F, which can be denoted by vector F equals summation I equals 1 to n vector Fi. According to work energy theorem, the work done by the resultant force F will be equal to change in kinetic energy of the particle. So we can write integral vector F dot dr along the curve equals half mv square. If we consider the force F as the summation of all forces acting on the particle, we write the equation as integral summation Fi from I to n along the curve dot dr equals half mv square. The equation is also expressed as the summation of work done by every individual force equals to change in kinetic energy. So let's write the work done by the force Fi as Wi. So in this case we will write the equation as summation Wi, which is the work done by individual forces summation, equals half mv square. Work done by force of different types. First, constant force. Let's evaluate the work done by a constant force. A force is constant when its magnitude is constant and direction is fixed. Example, gravitational force near Earth's surface, kinetic friction force between fixed surface and direction of relative velocity. A. Work done by gravitational force near Earth's surface, which is an example of constant force. So consider a mass block initially at rest falls from a height h. The only force acting on the body is gravitational force. If we neglect the air drag, the gravitational force is acting downward direction and displacement is also in downward direction. So the gravitational work will be equal to integral 0 to h vector f dot vector dy. If we write the force in vector form as minus mg j cap dot, the displacement is minus dy j cap, we are considering upward as positive. So we get the work done as mgh. The work done can also be obtained by using work energy theorem. Using work energy theorem, the work done by gravitational force will be equal to change in kinetic energy. The kinetic energy change is equal to half mv square minus 0, which equals half mv square. And from kinematics we know that the velocity v equals root 2 gh. So if we put the value of velocity v root 2 gh, we will get the gravitational force work done equals half m root 2 gh whole square, which equals mgh. Now let's take another example of constant force, which is frictional force or kinetic frictional force rather. So consider the situation: a body of mass m slides on a rough surface of table. The kinetic friction force of magnitude mu n acts on the body in the direction opposite to its relative velocity with respect to the rough surface of table. The direction of displacement of the body and the force are opposite to each other. Assuming the motion in positive x direction, the kinetic friction force is written as vector Fk equals minus mu mg I cap, because the frictional force is acting in the opposite direction of motion. The displacement of body is vector d equals x I cap. The work done by frictional force will be vector F dot vector d integral along the curve C. So if we integrate the vector F dot d, we will get minus mu mgx. So this is the work done by the kinetic friction force. If the mass body is again brought back to initial position, the same amount of work is done by the kinetic friction force. The total work done by kinetic friction force in a round trip is minus mu mgx minus plus minus mu mgx, which equals minus 2 mu mgx. The non-zero value of work done by kinetic friction force suggests that it is a non-conservative force. Spring force. Consider a massless spring. The spring length when the force on it is 0, also called natural length, is L. Connect one end of the spring with fixed support and set other end free. Let's apply small amount of force at the free end in the direction along spring so as to elongate the spring. As the external force is applied to spring, the spring gets elongated slightly. The spring develops a restoring force acting in the direction opposite to the direction of application of external force, which tries to restore its natural length. The magnitude of this force is observed to be proportional to change in length of spring. Let's consider the time t when spring is elongated by a length x. At this moment, the restoring force of spring is written as vector F is SPR equals minus kx I cap. The value of k depends on the material property, spring geometry, and only these two things. Hooke's law can be used to establish a relation between the forces and displacement of the free end. So, as the spring gets displaced from natural length, the restoring force does work. Let's evaluate that work. So the restoring force is minus kx and the displacement is dx. If we integrate this expression from 0 to x, we will get the work done by spring force as minus half kx square. The spring potential energy will be negative of the work done by the conservative force, which is the spring force. So the spring potential energy will be half kx square. Variable force. A force is said to be variable when its magnitude, direction, or both varies with respect to space or time coordinates. Such forces are represented by vector point function whose value is unique at every coordinate in the given region of space. A force vector F equals Fx I cap plus Fy j cap plus Fz k cap is a variable force if any of the component of the force varies with space or time. We write vector F equals vector F x y z t. It has three components: vector fx, which is fx equals fx x y z t, fy and fz, all varying with the x y z and t independent variables. Consider the simple case when the force magnitude is varying with respect to only x coordinate. So we can write vector f equals to vector fx. Let's assume the fixed direction of force towards positive direction of x-axis. Work done by this variable force is the area of the region below the curve as shown in the figure. So we evaluate the work done by integrating vector f dot dx, and we obtain the formula from x1 to x2 fx dx. The area below the curve can also be obtained by numerical approximation, and this method can be used to evaluate the work done numerically. Divide the region below the curve into n number of equal width regions as shown in the figure. Let's assume each region as rectangle. Increase the number of rectangles to improve accuracy. Each rectangle will have the width delta x equals x2 minus x1 divided by n. The height of the ith rectangle will be approximately equal to vector function f x1 plus I minus 1 delta x. The work done by the force of magnitude fx will be summation of all the small rectangle areas. So this will be equal to summation I equals 1 to n f x1 plus I minus 1 delta x multiplied by delta x. Now let's consider the work done by a general three-dimensional variable force. Work done by a general three-dimensional variable force is obtained by obtaining the line integral of the force along the curve along which the particle is displaced. Now let's discuss about gravitational potential energy. Earlier we have defined the potential energy as negative of the work done by conservative force. So work done by gravitational force in the round trip is 0. So we already concluded that the gravitational force is a conservative force. So as we conclude that the work done by gravitational force is a conservative force, so we can define that the gravitational potential energy will be negative of the work done by the conservative gravitational force, and we can write uf minus ui equals minus of integral I to f vector f gravity dot displacement dr. The gravitational force is expressed as, from Newton's law of gravitation, vector f gravity equals minus g mm divided by r square vector r cap, which is a unit vector. So if we put this value in the expression of work done, we will get the work done as minus integral I to f g mm divided by r square dr, which equals g mm 1 by rf minus 1 by ri. At altitude h, the value of Ri will be r plus h, where r is the radius of earth. At the altitude 0, the Rf value will be equal to the radius of earth. The work done by gravity is evaluated as W gravity equals g mmh divided by r square multiplied by 1 plus h by r to the power minus 1. If we expand the value inside the bracket, we will get 1 minus h by r. So the term W gravity will become g mmh divided by r square minus g mmh square by r cube. Let's call this as equation 1. The value of g is 6.674 multiplied by 10 to the power minus 11 nm square by kg square, and the mass of earth is 5.97 into 10 to the power 24 kg. The radius of earth is 6.371 multiplied by 10 to the 6 meter. So if you put these values, and the value of h by r can be neglected if the value of h is very small as compared to r. So if you neglect the term h by r with respect to the term 1, we will get the work done by gravity as g mmh divided by r square. The term g is gm by r square is called acceleration due to gravity near Earth's surface. Its value is evaluated as g equals gm by r square, which equals to 6.674 multiplied by 10 to the power minus 11 multiplied by 5.97 multiplied by 10 to the power 24 divided by 6.371 whole square multiplied by 10 to the power 12 meter per second square, which equals to 9.81624 meter per second square. The initial point is assumed as the reference point and the gravitational potential energy corresponding to this point is assumed as 0. The gravitational potential energy is evaluated considering the initial point as reference, and we write the gravitational potential energy U gravity equals minus of W gravity, which equals minus mgh. So we see that the work done is mgh and gravitational potential energy is minus mgh, which can be described here. In the above derivation, we took the initial reference point at altitude h and the final gravitational potential energy of mass with respect to this point is evaluated as minus mgh. So at altitude h we assumed the gravitational potential energy to be 0 and it is assumed as the reference point, and the final potential energy which is at the earth's surface will be equal to minus mgh. Conservation of mechanical energy. The work energy theorem states that work done by the resultant force equals change in kinetic energy. The resultant force is sum of all the forces acting on the particle, which includes the conservative forces, non-conservative forces and external forces. Principle of conservation of mechanical energy. If work done by external force and non-conservative force is 0, then the mechanical energy of the system remains conserved. So we can write Wc plus Wnc plus Wext equals delta K. The work done by conservative force is defined as negative of change in potential energy. Therefore, the above equation can be written as minus delta U, which is the work done by conservative force, plus Wnc plus Wext equals delta K. So if we take minus W term in right hand side, we will get Wnc plus Wxt equals delta K plus delta U, the kinetic energy change plus potential energy change, which will be equal to the total mechanical energy change. So work done by non-conservative force and work done by external force equals change in the mechanical energy. If let's consider the situation when work done by non-conservative force and work done by external force is 0. In that case, we will get the left hand side as 0, and in this situation the above equation reduces to delta E equals to 0, which is the principle of conservation of mechanical energy, which states that if the work done by external force and non-conservative force is 0, the total mechanical energy of the system remains unchanged. This is also called as principle of conservation of mechanical energy. Spring mass system. The spring mass system shown in the figure is placed on a frictionless table. The initial configuration of the system is such that the spring is elongated from its natural length by a length x. As the system is released, the spring force acts on the direction opposite to the elongation. The only force which does work is the spring force, which is a conservative force. Therefore, we can conclude W external plus W non-conservative equals 0 and total mechanical energy of the system is conserved. Let's use principle of conservation of mechanical energy to evaluate the velocity of mass block when the spring comes to natural length. So we will write initial mechanical energy of the system equals final mechanical energy of the system. The initial mechanical energy of the system includes only spring potential energy. So we write half kx square, and final mechanical energy of the system has no potential energy, only the kinetic energy half mv square. So we equate these two terms and we get the velocity of the mass attached to the spring at natural length v equals square root of k by mx. This is the velocity of mass which is attached to the spring at the natural length of spring. Power. The rate with which a force does work is called power. It is also defined as the rate with which kinetic energy of body increases. We write P equals dW by dt. Also we can write P equals d of F dot dr divided by dt, which equals to vector F dot vector V, where vector F is the force, external force, and vector V is the velocity of the particle at any instant of time t. So this formula gives the instantaneous power generation or power consumption. Let's solve a question. A uniform ball of radius r rolls without slipping down from the top of a sphere of radius r. Find the angular velocity of the ball at the moment it breaks off the sphere. The initial velocity of the ball is negligible. So let's draw a free body diagram at angle theta from the top position, and the forces acting at this position on the ball are the gravitational force, which has the component mg cos theta and mg sin theta in the direction as shown, and the normal force which has the acting in the outward direction, radially outward direction. So we'll write the equation of the ball which is executing a circular motion as mg cos theta minus n equals m omega naught square r plus r. Let's call this as equation 1. When the ball breaks off the sphere, the normal components become 0. So we equate n to 0 and we get the angle cos theta as cos theta equals omega naught square r plus r divided by g. Let's call this as equation 2, and from the constraint of sphere we get the relation between two angular velocities omega naught equals omega r divided by r plus r. Let's call this as equation 3. From equation 2 and equation 3 we can write cos theta equals omega square r square divided by r plus rg. Let's call this as equation 4. The conservation of mechanical energy between initial point and breakoff point gives the equation mgr plus r equals mgr plus r cos theta plus half mv square plus half I omega square. On simplification, we get gr plus r equals gr plus r cos theta plus 0.7 r square omega square. On further simplification, on putting the value of cos theta from the equation which shown in the earlier equation, cos theta is evaluated as omega naught square r plus r divided by g. So if you put the value of cos theta, we will get gr plus r equals gr plus r multiplied by omega square r square divided by r plus rg plus 0.7 r square omega square. On simplification, we get gr plus r equals 1.7 r square omega square, and in the next step we get omega equals square root of 10 g r plus r divided by 17 r square. So this is the angular velocity of the ball with which it breaks off the sphere.